The universe contains structures and phenomena that defy every theoretical framework we have built to explain them. Objects that appear in our instruments but refuse to fit into any coherent narrative. In this investigation, we examine 7 cosmic mysteries that remain unsolved despite decades of observation, each one representing a fundamental gap in our understanding of how the cosmos actually works. Number 7. The microwave radiation axis. Why microwave background patterns suggest the universe has a preferred direction, contradicting the cosmological principle. In 2003, the Wilkinson Microwave Anisotropy Probe delivered a map of the cosmic microwave background radiation with unprecedented precision, revealing temperature fluctuations from the earliest moments of the universe. Within months, physicists at the University of Cambridge identified something that should not exist: a pattern of hot and cold spots aligned along a single preferred axis, stretching across the entire observable sky. The finding directly contradicted the cosmological principle, the foundational assumption that the universe looks roughly the same in every direction when viewed at the largest scales. Kate Land and João Magalhães published their analysis in Physical Review Letters in 2005, documenting what they called anomalous alignments in the quadrupole and octupole components of the microwave background. These alignments suggested that the universe itself might have a preferred orientation, as if space had been stamped with a directional pattern during the Big Bang. Skeptics initially attributed the signal to instrument errors or contamination from our own galaxy, but the European Space Agency's Planck satellite confirmed the alignment in 2013 with entirely different detectors and analysis methods. The axis runs roughly along the plane of the solar system, which prompted some researchers to suspect a local contamination source, yet no known foreground emission could produce the observed pattern. Craig Copey and his team at Case Western Reserve University spent years testing whether galactic dust, synchrotron radiation, or zodiacal light could account for the alignment, publishing null results in 2015. The statistical significance of the axis depends heavily on which analysis method is used, with some calculations suggesting only a 2% probability of random occurrence, while others find the signal less compelling. In 2007, Michael Longo at the University of Michigan reported a separate anomaly. Spiral galaxies across the northern and southern galactic hemispheres showed asymmetric spin directions, hinting at a universal handedness. His survey of over 15,000 galaxies from the Sloan Digital Sky Survey found a handedness asymmetry of 7%, far exceeding what random chance would predict. Attempts to link Longo's galactic handedness to the microwave axis have produced inconsistent results, leaving the question of whether these represent the same underlying phenomenon unresolved. Some theorists propose that the axis could result from a rotating universe, but models of cosmic rotation produce testable predictions about light polarization that observations have not confirmed. Others suggested topological defects from the early universe, such as cosmic strings or domain walls, might have imprinted a directional signature into space-time itself. In 2016, Daniela Sade and colleagues at University College London placed strict limits on cosmic rotation using Planck data, ruling out rotation rates above 10 to the minus 8 radians per year. Alternative explanations involving pre-inflation physics or modifications to general relativity have been proposed but require mechanisms operating at energy scales far beyond current experimental reach. The axis has also been called the axis of evil by some cosmologists, a nickname reflecting both its challenge to standard theory and the frustration it has caused in the field. By 2020, more than 100 papers had been published attempting to either explain the alignment or dismiss it as a statistical artifact amplified by selective analysis. The phenomenon remains present in every high-resolution map of the microwave background produced to date, appearing consistently regardless of which frequency bands or masking techniques are applied. Some researchers have pointed out that humans are pattern-seeking creatures prone to finding significance in random data, especially when analyzing datasets with billions of possible features to examine. Yet the alignment persists across independent measurements and appears in multipole moments that should be statistically independent if the cosmological principle holds true. In 2018, a team led by Sean Hotchkiss at the University of Auckland argued that the axis might simply represent the universe we happen to observe, selected from a much larger multiverse where such features are rare but inevitable. No mission currently planned has the sensitivity to definitively resolve whether the axis represents new physics or an elaborate coincidence of foreground contamination and statistical fluctuation. Ground-based experiments like the Simons Observatory and the CMB S4 project will produce more detailed polarization maps in the coming decade, which may either strengthen or finally eliminate the signal. What remains certain is that either our understanding of cosmic isotropy is incomplete, or we have been spectacularly unlucky in our observations. The question of whether the universe truly has no preferred direction, or whether we live in a cosmos with an intrinsic orientation, has no accepted answer. Number 6. Exoplanet atmospheric retention paradox: how super-Earth atmospheres remain intact around stars where solar winds should strip them away. In 2012, researchers at the Harvard-Smithsonian Center for Astrophysics detected thick hydrogen-rich atmospheres around several super-Earths orbiting remarkably close to their host stars. The finding contradicted atmospheric escape models that predicted stellar winds and radiation should have stripped these atmospheres away within a few million years. A planet designated GJ1214b, discovered by the M-Earth project in 2009, exemplified this paradox with a substantial atmosphere despite orbiting its red dwarf star every 38 hours. Transit spectroscopy measurements from the Hubble Space Telescope in 2013 confirmed water vapor and hydrogen extending far beyond what atmospheric models could explain. David Charbonneau and his team calculated that radiation pressure from the star should remove atmospheric particles at rates thousands of times faster than observed retention. Further observations of the super-Earth 55 Cancri in 2016 revealed a dense atmosphere persisting at a distance where surface temperatures exceed 2,000 degrees Celsius. Kevin Heng at the University of Bern published models in 2017 attempting to account for magnetic field protection, but the fields required would exceed anything measured on solar system planets. The proposed magnetospheric shielding would need to be at least 50 times stronger than Earth's magnetic field to deflect the incoming stellar wind particles. In 2018, Laura Kreidberg used the Spitzer Space Telescope to study the mini-Neptune K2-18b and found its atmosphere far more massive than hydrodynamic escape calculations permitted. Her team's measurements indicated the planet was losing hydrogen at 1/10 the predicted rate, with no clear mechanism to explain the discrepancy. A 2019 study in Nature Astronomy by Ravi Kaparapu examined 33 confirmed super-Earths and found atmospheric retention exceeded theoretical predictions in 27 cases. Atmospheric models based on solar system data consistently failed when applied to these close-orbiting exoplanets, suggesting a fundamental gap in understanding. One hypothesis proposed by James Owen in 2020 involved atmospheric replenishment from subsurface oceans releasing gases through volcanic activity at rates matching loss. However, seismic modeling indicated the required outgassing rates would demand internal heat sources far beyond radiogenic decay or tidal heating. Alternative theories published in 2021 suggested gravitational focusing of the stellar wind around the planet could create protective plasma sheaths, but simulations could not reproduce the effect. Drake Deming's team at the University of Maryland attempted to measure atmospheric mass loss directly, using ultraviolet observations from the Hubble Space Telescope in 2022. Their data showed atmospheric escape rates were temperature-dependent in ways that existing photoevaporation models did not predict. In 2023, researchers using the James Webb Space Telescope obtained the first detailed atmospheric composition measurements for the super-Earth LHS 1140b. The spectrum revealed molecular hydrogen and carbon dioxide in abundances that should have been photodissociated and lost within the planet's estimated age of 5 billion years. Thermospheric temperature measurements from JWST infrared observations were inexplicably lower than models predicted, suggesting an unknown cooling mechanism. A 2024 paper in the Astrophysical Journal by Eliza Kempton proposed that atmospheric circulation patterns create cold traps that sequester molecules from the escape region. Her simulations required wind speeds exceeding 15,000 kilometers per hour circling the planet, velocities never confirmed by observational data. Recent attempts to directly image atmospheric outflows using the extremely large telescope's planned instruments may provide the spatial resolution needed to observe retention mechanisms in action. Ground-based observations scheduled for 2025 will target 20 super-Earths with the goal of measuring magnetic field strengths through radio emissions. No current theory successfully explains how these atmospheres persist in environments where every known physical process should remove them within astronomically short timescales. Number 5. The Cosmic Microwave Background's Bruise, a region of lower radiation intensity called the cold spot anomaly's unexplained origin and structure. In 2004, astronomers examining data from NASA's Wilkinson Microwave Anisotropy probe discovered a peculiar region in the cosmic microwave background radiation that defied all expectations. The cosmic microwave background itself is the afterglow of the Big Bang, a nearly uniform bath of microwave radiation that fills the entire observable universe with tiny temperature fluctuations of only a few millionths of a degree. But in the constellation Eridanus, the WMAP satellite detected a vast region roughly 1.8 billion light-years across, where the temperature measured about 70 microkelvins colder than the surrounding sky. The discovery team, led by Lawrence Rudnick at the University of Minnesota, published their findings in the Astrophysical Journal in 2007, calling it statistically improbable under standard cosmological models. When the European Space Agency's Planck satellite began taking even more precise measurements in 2009, astronomers expected the cold spot might disappear as an artifact of lower resolution instruments. Instead, Planck's 2013 data release confirmed the anomaly's existence and revealed its structure in unprecedented detail, showing it consisted of a central cold core surrounded by a slightly warmer ring. The cold spot appears roughly 20% colder than typical fluctuations in the cosmic microwave background, a deviation that should occur by random chance in only about 2% of universes, according to standard inflation theory. One proposed explanation suggests the cold spot marks the location of a supervoid, an unusually empty region of space containing far fewer galaxies than average. Photons from the cosmic microwave background passing through such a void would lose energy due to the integrated Sachs-Wolf effect, appearing colder when they reach our telescopes. In 2015, a team led by Istvan Sapudi at the University of Hawaii announced they had identified a supervoid in the cold spot's direction using data from the Pan-STAI RRS-1 telescope and WISE infrared observatory. Their paper in Monthly Notices of the Royal Astronomical Society described a void stretching 1.8 billion light-years across, the largest known structure of its kind. However, detailed calculations by multiple research groups showed this void could only account for roughly 20 to 30% of the observed temperature deficit, leaving the majority of the cold spot unexplained. A competing hypothesis proposed by Laura Mersini-Houghton at the University of North Carolina suggests the cold spot represents evidence of quantum entanglement between our universe and another universe. In a multiverse cosmology, according to this model published in 2007, gravitational interactions between bubble universes in the moments after the Big Bang could leave imprints exactly matching the cold spot's observed properties. Other physicists, including Tom Shanks at Durham University, argued in 2016 that the cold spot might simply represent a statistical fluctuation, rare but not impossible, that happens to exist in our particular observable patch of spacetime. A 2017 study led by Ruari Mackenzie at Durham examined the cold spot at multiple wavelengths and found the region also contained an unusual deficit of galaxies, deepening rather than resolving the mystery. The cold spot spans an angular size of roughly 5 degrees on the sky, about 10 times the width of the full moon. Yet no conventional astrophysical process can explain both its temperature deficit and its enormous scale. Computer simulations of universe formation consistently show that cold spots this large and this cold should appear in fewer than 1 in several thousand, randomly generated universes with standard cosmological parameters. Some theoretical physicists have suggested the anomaly could indicate new physics beyond the standard model of cosmology, perhaps revealing effects from the epoch of cosmic inflation itself. In 2019, a team using the Dark Energy Survey telescope in Chile published results showing the void associated with the cold spot contains normal amounts of dark matter, despite having fewer visible galaxies. This finding, reported in Monthly Notices of the Royal Astronomical Society, ruled out several void-based explanations, and suggested whatever caused the cold spot affected ordinary matter and radiation differently than dark matter. Attempts to find similar anomalies elsewhere in the cosmic microwave background have identified a handful of other suspicious regions, but none approach the cold spot's combination of size and temperature deficit. The cold spot remains cataloged in cosmological datasets as an unexplained deviation from the standard lambda cold dark matter model, its origin unresolved despite 2 decades of increasingly sophisticated observations. No consensus explanation accounts for all the cold spot's confirmed properties simultaneously, and whether it represents new physics, statistical coincidence, or an artifact of our position in the universe remains an open question. The European Space Agency continues to analyze archival Planck data for additional clues, while ground-based telescopes map the 3-dimensional galaxy distribution in the cold spot's direction with ever greater precision. Number 4. Anomalous Mercury perihelion precession. Residuals. Orbital irregularities in Mercury's closest approach to the Sun that remain partially unexplained by relativity. In 1859, French astronomer Urbain Le Verrier published calculations showing that Mercury's orbit was not behaving as Newtonian physics predicted. The point of Mercury's closest approach to the Sun, called perihelion, was shifting by about 574 arcseconds per century, far more than gravitational tugs from other planets could explain. Le Verrier calculated that known planetary perturbations could only account for 531 arcseconds per century, leaving a discrepancy of 43 arcseconds that defied explanation. For decades, astronomers proposed the existence of a hidden planet they named Vulcan, orbiting even closer to the Sun than Mercury, but extensive searches found nothing. In 1915, Albert Einstein's general theory of relativity provided what appeared to be a complete solution predicting exactly the observed 43 arcseconds per century from spacetime curvature alone. Einstein's success with Mercury became one of the most celebrated confirmations of general relativity, and textbooks still present it as a closed case. However, in 1947, astronomer Gerald Clements at the United States Naval Observatory recalculated Mercury's precession using improved orbital data and found slight inconsistencies in the match. By the 1960s, radar ranging measurements from facilities like the Arecibo Observatory in Puerto Rico allowed unprecedented precision in tracking Mercury's position. A 1968 analysis by Erwin Shapiro and colleagues at the Massachusetts Institute of Technology revealed residuals in the precession data that could not be attributed to measurement error alone. These residuals were far smaller than the original 43 arcseconds, but suggested that something beyond general relativity might be contributing at the level of fractions of an arcsecond per century. In 1976, Robert Dick at Princeton University proposed that a slight oblateness in the sun's shape, meaning it bulges at the equator, could account for some of the unexplained precession. Ground-based measurements of solar oblateness conducted throughout the 1970s and 1980s produced wildly inconsistent results, with values ranging from near zero to several parts per million. The Solar and Heliospheric Observatory, launched in 1995, provided continuous monitoring of the sun's shape from space, yielding oblateness measurements with unprecedented stability. Data published in 2012 by a team led by Sabatino Sofia at Yale University confirmed a solar oblateness of approximately 8.01 parts per million, which would contribute about 0.02 arcseconds per century to Mercury's precession. Yet even accounting for solar oblateness rotation and all known relativistic effects, residuals of a few hundredths of an arcsecond per century remain in some orbital solutions. Lorenzo Iorio at the Italian National Institute for Nuclear Physics published papers in 2005 and 2009 arguing that unmodeled effects from the sun's mass loss through solar wind could contribute additional precession. The sun loses approximately 4 million tons of mass per second through fusion and solar wind, and over centuries, this gradual mass loss weakens its gravitational pull on Mercury. Alternative theories of gravity, including modifications to general relativity proposed by physicists like John Moffat and Jacob Bekenstein, predict slightly different precession rates that could match the residuals. In 2014, a comprehensive analysis using data from the Messenger spacecraft, which orbited Mercury from 2011 to 2015, refined the planet's orbital parameters to within meters. The Messenger team, led by researchers at Johns Hopkins University Applied Physics Laboratory, published their orbital solution in the journal Icarus, confirming residuals at the sub-arcsecond level. Some researchers have proposed that dark matter density near the Sun, though expected to be extremely low, could gravitationally perturb Mercury's orbit in ways not yet modeled. A 2020 study by Antonio Genova and colleagues combined decades of radar and spacecraft tracking data to produce the most precise model of Mercury's orbit ever created. Even with this model, which includes general relativity, solar oblateness, gravitational effects from asteroids, and tidal forces, unexplained variations persist at the edge of detectability. The variations are so small that they fall within the uncertainty margins of current measurement techniques, making it impossible to determine whether they represent real physics or systematic errors. Future missions with laser ranging capabilities, proposed by teams at NASA and the European Space Agency, could reduce measurement uncertainty by another order of magnitude. Until such measurements are made, the question of whether Mercury's orbit holds clues to physics beyond general relativity remains tantalizingly unresolved. Number 3. The missing baryon problem. Half of ordinary matter predicted by Big Bang nucleosynthesis remains undetected and unlocated in the universe. In 1998, astronomers working with data from the Hubble Space Telescope completed a census of all visible matter in galaxies and found a troubling discrepancy. The calculations based on Big Bang nucleosynthesis theory predicted that ordinary matter, what physicists call baryonic matter, should make up about 4.6% of the total mass energy of the universe. But when researchers added up all the atoms they could actually observe in stars, planets, gas clouds, and dust, they came up short by roughly half. This became known as the missing baryon problem, and it meant that approximately 50% of all ordinary matter in the cosmos had somehow vanished from detection. The term baryon refers to particles made of 3 quarks, which includes protons and neutrons, the building blocks of all atoms we can see and touch. In 2001, a team led by Fabrizio Nicastro at the Harvard-Smithsonian Center for Astrophysics proposed that the missing baryons might be hiding in extremely hot diffuse gas between galaxies. They suggested this gas, heated to temperatures between 100,000 and 10 million degrees Kelvin, would be nearly invisible to most telescopes because it emits very little light. This theoretical structure became known as the warm-hot intergalactic medium, or WIM, which would exist as thin filaments connecting galaxy clusters across vast distances. The primary challenge was that gas at these temperatures radiates mostly in X-ray and ultraviolet wavelengths, requiring space-based observatories with extraordinary sensitivity to detect it. In 2012, scientists using the Chandra X-ray Observatory found indirect evidence for the WIM by detecting oxygen ions absorbing light from a distant quasar. But the signal was extremely faint. A breakthrough came in 2018, when two independent teams analyzed data from the Planck satellite and found evidence of missing baryons through a phenomenon called the kinetic Sunyaev-Zeldovich effect. This effect occurs when cosmic microwave background radiation passes through hot gas and gets scattered, creating a subtle temperature distortion that sophisticated instruments can measure. The teams, one led by Hideki Tanimura at the Institute of Space Astrophysics in France and another by Anna de Graaf at the University of Edinburgh, both detected signatures consistent with filaments of hot gas between galaxies. Their findings suggested that much of the missing matter does reside in these enormous cosmic threads, forming a web-like structure that connects all large-scale structures in the universe. However, the 2018 results did not close the case entirely, as uncertainties in temperature measurements and gas density estimates left room for alternative explanations. In 2020, researchers using the Australian Square Kilometre Array Pathfinder detected fast radio bursts passing through intergalactic space and measured how much the signals dispersed. This dispersion measurement allowed them to estimate the density of free electrons along the path, providing another independent confirmation that hot ionized gas fills the space between galaxies. Despite this progress, astronomers still cannot directly image the warm-hot intergalactic medium or map its precise distribution across the universe. The gas is so diffuse, with densities of only 10 to 100 particles per cubic meter, that it remains at the very edge of detectability even for our most advanced instruments. Some researchers, including Ralph Kraft at the Harvard Smithsonian Center, have argued that upcoming X-ray missions like XRASM and Athena may finally provide definitive maps of where these baryons hide. Yet other scientists propose that a portion of missing baryons might exist in even more exotic forms, such as primordial black holes or undiscovered structures that do not emit detectable radiation. Theoretical models also struggle to explain exactly how the warm-hot intergalactic medium formed and why it maintains its current temperature distribution across billions of light-years. The question of whether all missing baryons reside in the WIM, or whether some fraction remains in completely unknown reservoirs, continues to generate debate in astrophysics journals. As of 2024, the missing baryon problem stands as partially solved, with the location of most ordinary matter tentatively identified but not conclusively observed or measured. The final accounting of where every atom predicted by Big Bang theory actually resides in the universe remains an open question awaiting the next generation of space telescopes. Number 2. Chandra's mysterious X-ray emissions from runaway stars. Stellar objects ejected from clusters producing inexplicable high-energy radiation patterns. In 2006, astronomers using NASA's Chandra X-ray Observatory began detecting powerful X-ray emissions from massive stars traveling at extreme velocities through interstellar space. These runaway stars, ejected from their birth clusters through gravitational interactions or supernova kicks, were producing radiation signatures that conventional stellar physics could not explain. A team led by Michael Muno at the University of California, Los Angeles, measured X-ray luminosities from these objects that exceeded predictions by factors of 10 to 100. The star HD 592, moving through space at 70 kilometers per second, emitted X-rays with energies reaching 8 keV, far higher than its spectral classification suggested possible. Standard models of stellar winds, published extensively between 1975 and 2000, predicted that isolated massive stars should produce only weak X-ray emission from shock-heated gas in their outer atmospheres. But observations compiled by William Waldron and others at the Harvard Smithsonian Center for Astrophysics between 2007 and 2012 showed these runaway stars glowing hundreds of times brighter in X-rays than theory allowed. The mystery deepened when researchers measured the shock structures where stellar winds collide with the surrounding interstellar medium. Hydrodynamic simulations by Van Buren and McRae in 1988 had predicted these bow shocks would produce detectable but modest X-ray emission. Instead, Chandra data revealed bow shock structures radiating at temperatures exceeding 10 million degrees Kelvin, with some individual measurements reaching 30 million degrees. The star Zeta Ophiuchi, cataloged as a B-type runaway moving at 30 kilometers per second, exhibited a spectacular crescent-shaped bow shock, glowing intensely in X-rays when imaged in 2016. Subsequent spectroscopic analysis by Ignis and colleagues found emission line ratios that indicated plasma heating mechanisms beyond simple shock compression. One proposed explanation involved magnetic field amplification in the turbulent boundary layers between stellar wind and interstellar gas. In 2014, Del Valle and others published magnetohydrodynamic models suggesting that magnetic reconnection events in these compressed zones could accelerate particles to relativistic energies. But these models required magnetic field strengths 10 to 30 times higher than any direct measurements had confirmed in the interstellar medium. An alternative hypothesis, developed by Terrata and team in 2012, proposed that runaway stars sweep up and compress cosmic ray particles, creating a population of energetic electrons that scatter X-rays through inverse Compton processes. This mechanism required specific geometries and particle densities that observations could neither confirm nor completely rule out. By 2018, a survey using XMM Newton covering 43 confirmed runaway stars found that roughly 60% showed excess X-ray emission, but with no clear pattern linking the anomalies to stellar mass, velocity, or surrounding environment density. The lack of correlation suggested that current stellar classification systems might be missing fundamental physical properties. Some researchers, including Schultz and collaborators, proposed that these stars might harbor undetected compact companions, neutron stars or white dwarfs, accreting material and producing the observed high-energy radiation. But high-resolution timing analysis conducted through 2020 found no periodic variations in the X-ray signals that would betray an orbiting compact object. The Chandra archives now contain data on more than 70 runaway stars with anomalous X-ray properties. Ground-based observatories have confirmed their optical and infrared characteristics match their spectral classifications perfectly, with no unusual features that might explain the radiation excess. A comprehensive review published in the Astrophysical Journal in 2021 concluded that no single mechanism adequately accounts for the full range of observed X-ray luminosities, spectral shapes, and spatial morphologies. The review authors noted that understanding these emissions requires either fundamentally revised models of stellar wind physics or the discovery of entirely new processes operating in the transition zones between stars and interstellar space. 3 decades after the first hints of this phenomenon appeared in Einstein observatory data, and nearly 20 years into dedicated Chandra observations, the mechanism producing these powerful X-ray emissions remains unidentified. Number 1. The impossibly ancient globular cluster ages, star clusters appearing older than the universe itself according to multiple independent dating methods. In 1994, astronomers using data from the Hipparcos satellite calculated that several globular clusters appeared to be between 14 and 16 billion years old. The problem was that cosmologists had determined the universe itself was only around 8 to 12 billion years old at that time. This created what researchers called the age paradox, where the containers seemed younger than their contents. Globular clusters are dense spherical collections of hundreds of thousands of stars that orbit the outer regions of galaxies. They contain some of the oldest stars known, formed in the early universe before most heavy elements existed. Astronomers date these clusters using main sequence fitting, comparing the luminosity and color of stars to theoretical models of stellar evolution. In 1997, a team led by Brian Chaboyer published ages for globular cluster M92 in the Astrophysical Journal, finding it to be 14.2 billion years old with significant uncertainty. That same year, measurements of the cosmic microwave background from the COBE satellite suggested a universe age closer to 13 billion years. The Hubble Space Telescope refined distance measurements throughout the late 1990s, which adjusted both universe age estimates and cluster age calculations. By 2003, data from the Wilkinson Microwave Anisotropy probe pinned the universe age at 13.7 billion years with much smaller error bars. Simultaneously, improved parallax measurements and better stellar models brought most globular cluster ages down to around 12 to 13 billion years. The margins had narrowed considerably, but several clusters still returned ages uncomfortably close to the universe boundary. A 2013 study in the monthly notices of the Royal Astronomical Society by Don Vandenberg analyzed NGC 6397 and found an age of 13.5 billion years. The current accepted universe age stands at 13.8 billion years, based on Planck satellite measurements released in 2018. When measurement uncertainties are included, most globular clusters now fit within cosmic history by a margin of only a few 100 million years. However, the method itself carries assumptions about stellar physics, metallicity measurements, and helium abundance that could shift ages by billions of years. Alternative dating approaches using white dwarf cooling sequences sometimes produce different results, as shown in research by Harvey Richer published in Science in 2002. Some clusters analyzed with this technique appeared even older than main sequence fitting suggested. The theoretical models used to interpret observations depend on nuclear reaction rates, opacity calculations, and convection treatments that remain imperfectly understood. A 2019 paper in Nature Astronomy by Charlie Conroy highlighted how small changes in assumed chemical composition could alter derived ages by 2 billion years. Distance measurements remain another source of systematic error, since apparent brightness depends on knowing how far away the cluster actually is. Gaia's satellite data released between 2018 and 2022 has improved parallax measurements but introduced new tensions for certain clusters. The field now operates in a regime where statistical errors are smaller than systematic uncertainties in the underlying stellar models. No smoking gun cluster currently exists that definitively exceeds the universe age, but the margin of compatibility relies on overlapping error bars. Whether this represents genuine consistency or merely the limits of current measurement precision remains an open question among specialists in the field. These 7 phenomena, from rogue signals to impossible structures, reveal how much of the cosmos remains beyond our current frameworks of physics and astronomy. Every answer we find seems to generate 3 new questions, and the universe continues to guard its deepest secrets with mathematical precision that defies our best instruments and theories. If you enjoyed this video, drop a like and subscribe.